With this methodology, we can also have virtual platforms, which are very useful because they can allow us to start software development before the hardware is ready. Something that we see a lot in the space domain is that missions take for a long time because first we need to wait until the hardware is ready before being able to develop the software. So this way we can break the hardware and software dependency for the development. Another concept which we employ in the Metasat project is the concept of virtualization. We are going to use a hypervisor in order to implement time and space partitioning. Also yesterday we had a very interesting talk about some lessons learned. And as we have seen, this can accelerate the development and the integration. The reason is that we can develop different components in isolation. They can be tested in isolation, and then they can be integrated together. And with this approach, we can also have easier fault detection, isolation, and recovery. So Metasat is going to be a 2-year project. As I said, started in January and will finish next year in December. We are focusing low TRL. We are going to rely on open source and standardized technologies because we want to avoid vendor lock-in, and we want to maximize interoperability. And we would like also to facilitate the development of a space ecosystem. We are going to use the open source model-based design tool, TASTE, which was designed by ESA and is constantly under heavy development with new enhancements. From our side, we are going to enhance TASTE with code generation capabilities for high-performance platforms like GPUs. Our hardware platform is going to be based on Noel 5, RISC-V based processors, which we will enhance with AI accelerator capabilities. And as I said, we will rely on virtualization, and we will allow the shared use of AI accelerators and GPUs from the hypervisor. And on the research side, we will focus on new AI approaches for integration testing and fault detection and isolation and recovery. In order to demonstrate our concepts, we will need a hardware platform. So this is an idea of the prototype platform that we are currently designing, the Metasat platform. It's going to be mixed criticality to support the concurrent execution of software of different criticalities. We're going to have a prototype on a Xilinx VC118, which is the biggest FPGA that we found that was able to fit both a multi-core and GPU. On the CPU side, as I said, we're going to have a multi-core Noel 5, which will be integrated with our Sparrow accelerator that I mentioned earlier. And the idea of this multi-core will be to accelerate high criticality software with moderate AI acceleration needs, with low latency, and through a qualifiable software stack. On the GPU side, we are going to have a RISC-V based GPU, which is called Vortex. That was an open source project started from Georgia Tech. We are going to enhance the GPU with features regarding the real-time execution. So currently, one of the limitations that we have in GPUs is that the execution of real-time workloads is limited. So we are going to have solutions for that. And GPU will be able to be used for software which requires higher performance that is not able to be provided by the CPU cluster. And still, we would like to have a qualifiable software stack, because one of the limitations that we have identified in our work, as I presented last year about the GPU4S project, is that currently GPU software relies on Linux and Android. But here we are going to have a driver that will be able to be used either by bare metal or from a real-time operating system like Artems. And we will also have the possibility to share the GPU among different partitions. The hardware platform will be open source, and much of the software that we will also develop will be also released as open source. Now, time to talk about Lagaro. This is the first RISC-V core that was developed in Spain. It's an academic design, 64-bit RISC-V, single issue. We have implementations both on the FPGA and as an ASIC, and has support for NACSI bus. It's capable of booting Linux, and this is a joint work not only from BSC but also from different institutions. And currently we are figuring out the legal details in order to open source it. Here you can see the different tape outs that we have performed so far with our Lagaro. We started back in 2019 with the first iteration in 65 in TSMC 65 nanometers, and our latest tape out was performed in back in December in 2022. Let's see a bit more of details for these designs. For the first iteration, it was a very simple processor in order, 5 stages, very similar to the one that we are taught in the computer architecture classes. Separate instruction and data caches and TLBs. And we submitted the design for tape out in May 2019. We got the first samples in September, and within 3 months we were able to boot Linux. For the second iteration, we have changed the instruction cache. In the first iteration, we were using the low risk SoC. So mainly we provided the RISC-V core, but gradually we are getting out of different components and we are implementing our own. So in the second iteration, we provided our own implementation of the instruction cache, and we included the performance monitoring unit. And that was also manufactured in TSMC 65 nanometers. For the third iteration, which we taped out in February 2022, we made the pipeline deeper. We included a short vector unit of 128 bits. And we had also our custom instruction cache and performance monitoring unit. And that was manufactured in Global Foundries 22 nanometers. And here is the fourth tape out, what we call Lagaro K. This is a higher performance processor with a two-way out of order superscalar architecture. The pipeline is even deeper with 11 stages, and we have also a configurable branch predictor. We have also a hit under miss for the accesses in the cache, and also configurable sizes for instruction and data cache. Actually, another thing that it's very interesting in this tape out is that in the same chip we have both a Lagaro Sargantana and an out of order core, so we are able to choose which one we want to boot. Here you can see a high-level picture of the core. In addition to the two cores, the Lagaro K and Sargantana that I mentioned, with their own private instruction and data cache, We have some accelerators. So we have an accelerator for genomics, so for accelerating DNA sequencing. We have Soria, which is an automotive accelerator for object detection, a post-quantum computing, and a microcontroller. Now I will talk a bit about some more designs that we have performed in BSC that are not so focused on space, but mainly on HPC, but maybe one day will be able to be incorporated in space designs. As I said, in European Commission, there is a lot of investment for non-dependence. And one of these programs, it's called European Processor Initiative. The idea for this is to develop European supercomputing technologies that we can use later, not only for supercomputing, but also for other strategic industries that we have in Europe. For example, our flagship industry is the automotive. This project is organized in what we call 3 different streams. In the first one, we focus on software and benchmarking. The second one is about the development of a general purpose processor. And the third stream, which is the most interesting one, and I would like to talk about, is the European Processor Initiative Accelerator. This is also based on RISC-V, and this is a European design, not only by BSC, but also other companies and institutions participating. Here you can see the timeline of this project. So it was started in 2019. In 2022, we had the first submission of the accelerator for manufacturing. And the plan is by 2024 to have the first generation of the general purpose processor plus the second generation of the accelerator. And by 2025, we would like to see this technology used in European supercomputers. Here you can see the high-level picture of the RISC-V accelerator of EPI. It's a self-hosted RISC-V CPU with wide access vector processing unit, 256 elements wide. And this is compliant with the RISC-V vector specification, the 0.7 and the 1. In order to maximize interoperability, we rely on the open vector interface. This is a RISC-V interface which was proposed jointly by Semidynamics and Barcelona Supercomputing Center, and allows to connect this vector processing unit to any RISC-V core that complies with this vector interface. Here we can see the extended BSC chip roadmap. You can see how we started here with Lagaro. You can see 2 different areas. Below we have CPUs, and on top we have accelerators. And as we go up, the complexity of the design increases. And here we can see the time. So we started with Lagaro with very simple design. And as we have seen from the previous slides, gradually we were increasing the complexity of the designs. And you can see that we have a lot of new chip tape outs planned for the next couple of years until we reach our goal of having supercomputing technologies based on RISC-V. So with that, I would like to conclude my presentation. I have shown you that at BSC we have a lot of experience in space processor design and evaluation. We have seen that RISC-V has opened the door for a lot of new opportunities in many different domains, and specifically on the space sector. And currently at BSC, we have a lot of ongoing activities ranging from purely academic and educational designs up to high TRL designs. We have open sourced a lot of designs, and we will keep doing so. And our hope is to be able to influence the way that next generation space processors technologies are going to be designed. So I would like also to give credit to a lot of people that have been involved in the projects that I presented. Not only the managing people, but mainly our students that do the hard work. And of course, I would like to acknowledge all the funding agencies that